Good morning, one and all. I am Dr. Kiran Kumar Ganta, working as Assistant Professor in the Department of Basic Science and Humanities. Today, I am going to teach Applied Physics subject, and the topic name is Carrier Concentration of Intrinsic Semiconductor, that is, Intrinsic Carrier Concentration. In the last class, we have derived the carrier concentration of intrinsic semiconductor in terms of density of electrons in conduction band and the density of holes in the valency band. Density of electrons in conduction band is denoted by N. We have derived it. Density of electrons in conduction band N is equals to 2 into 2 pi me star kt by h square to the power of 3 by 2 exponential of EF minus EC by kt. So this is the density of electrons in conduction band of an intrinsic semiconductor. We have done it in the last class. Also, we have derived the expression for density of holes in the valency band, that is denoted by P. P is equals to 2 into 2 pi mh star kt by h square to the power of 3 by 2 exponential of EV minus EF by kt. These two derivations have been covered in the last class. One is density of electrons in conduction band. The second one is density of holes in the valency band. Here me star is the effective mass of electron, K is the Boltzmann's constant, T is temperature, EF is Fermi energy, EC is the bottom of the conduction band, that is the lowest energy level of conduction band, and ms star is effective mass of hole, again K is the Boltzmann's constant, T is temperature, EF is top of the valency band, that is the highest energy level of valency band, again EF is the Fermi energy. So in this class today I am going to derive the expression for carrier concentration of intrinsic semiconductor using law of mass action. So law of mass action says Ni square is equals to N into P. Right? Square of carrier concentration of intrinsic semiconductor is the product of density of electrons in conduction band and density of holes in the valency band. So this is known as law of mass action. So using law of mass action, we are going to derive the carrier concentration of intrinsic semiconductor. So using law of mass action, we can write Ni square is equals to N into P. So now I am writing the expression for N, that is 2 into 2 pi me star kt by h square to the power of 3 by 2 exponential of EF minus EC by kt. So this is for N. For P, again 2 into 2 pi mh star kt by h square exponential of EV minus EF by kt. Here 2 into 2 4 and 2 pi kt by h square is a common term. So now this term can be written as 4 into 2 pi kt by h square to the power of 3. 3 by 2 plus 3 by 2 is 3. Then me star mh star to the power of 3 by 2. Here we can combine both the exponent terms because e power x into e power y is equals to e to the power of x plus y. So both the terms can be combined. Then it can be written as exponential of EF minus EC plus EV minus EF by kt. Here EF gets cancelled. So this can be written as 4 into 2 pi kt by h square to the power of 3 me star mh star to the power of 3 by 2 exponential of minus EC plus EV KT. Here generally energy gap. What is energy gap of the material? Let us say this is a conduction band. A conduction band is a band which is the higher energy level, next higher energy level of the valency band. The bottom of the energy level, the bottom of the conduction band is denoted by EC, and the top of the valency band is denoted by EV. Means the highest energy level of valency band. Generally, the valency band is formed by series of energy levels which contains the valence electrons. So the energy difference between EC and EV is known as energy gap of the material. So energy gap EG is equals to EC minus EV. So we can write here E minus EC plus EV. So this can be written as minus EG. Then this term can be written as 4 into 2 pi KT by H square to the power of 3 ME star MH star to the power of 3 by 2 exponential of minus EG by KT. So this is for Ni square. Ni square is equals to 4 into 2 pi KT by H square power of 3 ME star MS star power of 3 by 2 exponential of minus EG by KT. This is for Ni square. But we are deriving intrinsic carrier concentration. So we have to take Ni only. Ni is a carrier concentration of intrinsic semiconductor. Then I am writing expression for Ni. Then root 4 is 2. So 2 into 2 pi KT by H square to the power of 3 by 2. Again already M 3 by 2 is there. Then ME star MH star to the power of 3 by 4. Then exponential of minus EG by 2 KT. So this is a expression of carrier concentration of intrinsic semiconductor. So this is a final expression of intrinsic carrier concentration. Very simple, very easy to understand. In the last class, we have derived the expression for density of electrons in conduction band. To understand this better, watch the last videos, first video. And this is the expression for density of holes in the valency band. We have derived it in the last class. Refer the last videos. So using law of mass action, Ni square is equals to N into P. Law of mass action says the square of carrier concentration of intrinsic semiconductor is the product of density of electrons in conduction band and density of holes in the valence band. Just substitute N and P expressions here. Just use simple mathematical simplification. Then we'll get this final expression. Ni is equals to 2 into 2 pi KT by H square whole power of 3 by 2 ME star MS star whole power of 3 by 4 exponential of minus EG by 2 KT. So this is the expression for intrinsic carrier concentration. Next we will derive the expression for Fermi level. Fermi level of intrinsic semiconductor. Fermi level of intrinsic semiconductor. Intrinsic semiconductor. Basically, an intrinsic semiconductor is a pure semiconductor which does not have any kind of impurities. It behaves like an insulator at 0 Kelvin and behaves like a conductor at higher temperature. In intrinsic semiconductor, density of electrons in conduction band is equals to density of holes in the valence band. Again, we have to write two expressions. One is density of electrons in conduction band. The second expression, density of holes in the valence band. So from the previous classes, density of electrons in conduction band is equals to 2 into 2 pi ME star KT by H square to the power of 3 by 2 exponential of EF minus EC by KT. Yeah, this is the expression for density of electrons in conduction band, that is N. And now I am writing the expression for density of holes in the valency band, that is P. Then 2 is equals to 2 pi MH star KT by H square to the power of 3 by 2 exponential of EV minus EF by KT. Right? Here 2 gets cancelled, and 2 pi KT by h is also a common term that can be cancelled. Then the remaining expression can be written as ME star to the power of 3 by 2 exponential of EF minus EC by KT is equals to MS star to the power of 3 by 2 exponential of EV minus EF by KT. Now rearrange this expression, means taking exponential terms one side, then this can be written as exponential of EF minus EC. You're already on the right hand side plus EV. If you take it to the left hand side, it will be minus EV plus EF by KT. This is equals to MH star by ME star to the power of 3 by 2. Right? Taking natural logarithm on both sides, this can be written as EF plus EF, 2EF minus of EV plus EC by KT is equals to natural logarithm ln MH star by ME star to the power of 3 by 2. So now this term can be written as 2EF EV plus EC is equals to 3 by 2 KT, 3 by 2 KT natural logarithm ln MH star by ME star. Now again it can be written as 2EF is equals to EV plus EC plus 3 by 2 KT ln MS star by ME star. Now I am writing the final expression for Fermi energy. Final expression Fermi energy EF is equals to EV plus EC by 2 plus 3 by 4 KT ln MS star by ME star. So this is a final expression for Fermi energy in intrinsic semiconductor. Fermi energy in intrinsic semiconductor. This is a final expression. EF is equals to EV plus EC by 2 plus 3 by 4 KT ln MS star by ME star. But at T is equals to 0 Kelvin, means at temperature T is equals to 0 Kelvin, if the T is equals to 0 Kelvin, this term will be 0. Then Fermi energy EF is equals to EV plus EC by 2. At T is equals to 0 Kelvin, Fermi energy EF is equals to EV plus EC by 2, which means the Fermi level exists at the middle of valence band and conduction band. Means it exists at the middle of the energy gap of the material. If we see the band diagram, energy band diagram, let us say this is a conduction band and this is a valence band. The highest energy level of valence band is denoted by EV The lowest energy level of conduction is denoted by EC. So in intrinsic semiconductor, Fermi level exists at the middle of conduction band and valence band. At T is equals to 0 Kelvin. T is equals to 0 Kelvin. But as temperature increases, probability means Fermi energy also increases towards the conduction band. Reason, by taking energy, electrons may excite from valence band to conduction band, first reason. And as temperature increases, effective mass of electron is less than effective mass of hole, which means effective mass of electron increases than effective mass of hole. Hence, the Fermi level increases towards the conduction band. So this is a variation of Fermi level with respect to temperature. That is, T is with respect to temperature as Fermi energy also increases. So this is about Fermi energy, Fermi level in intrinsic semiconductor. Very simple, easy to derive it. First we have to take the density of electrons in conduction band is equal to density of holes in valence band. Straight away we have taken the two expressions, density of electrons in conduction band and the density of holes in the valence band. Just by equating it, we get the final expression, that is EF is equals to EV plus EC by 2 plus 3 by 4 KT log Ma star by Me star. At T is equals to 0 Kelvin, the term will be 0. Then the Fermi energy EF is equals to EV plus EC by 2, which means at T is equals to 0 Kelvin, the Fermi level exists at the middle of conduction band and valence band. Means it exists at the middle of the energy gap of the material. But as temperature increases, Fermi level also increases towards the conduction band. This is Fermi level. Next, we will derive the electrical conductivity of intrinsic semiconductor. Electrical conductivity. Electrical conductivity intrinsic semiconductor. Generally, electrical conductivity is denoted by sigma. Sigma, right? So this is a general expression for sigma. Electrical conductivity sigma is equals to Ne mu. This is a general expression. This is a relation between conductivity and mobility. Here mu is a mobility and sigma is electrical conductivity. But in intrinsic semiconductor, current is carried by the electrons and holes. Then this can be written as sigma is equals to sigma I is equals to sigma E plus sigma H. Here the sigma I is electrical conductivity intrinsic semiconductor. Sigma E is due to the electrical conductivity to the electrons. Sigma H is electrical conductivity due to the holes. We can write P also, no problem, or we can write H also. Okay. Then this term takes the form sigma I is equals to Ne mu E plus Pe mu H. So this term is due to the electrons, this term is due to the holes. But in intrinsic semiconductor, Ni is equals to N is equals to P. Then sigma I can be written as sigma I is equals to Ni E into mu E plus mu H. Since N is equals to P is equals to Ni. So N and P are equal. Here Ni is a carrier concentration of intrinsic semiconductor. E is a charge of electron. Mu E and mu H are the mobility of electrons and holes respectively. So here we have to write the expression for carrier concentration of intrinsic semiconductor. So this is a carrier concentration of intrinsic semiconductor. So we have to write this expression. Carrier concentration of intrinsic semiconductor. So I am writing this expression here. Ni expression. Then sigma I is equals to 2 into 2 pi KT by H square to the power of 3 by 2 Me star Mh star to the power of 3 by 4 exponential of minus Eg by 2 KT. Here Eg is energy gap of the material. Then this is a Ni expression. then E into mu E plus mu H. Right? Just I have written the carrier concentration of intrinsic semiconductor expression. This expression straight away. As 2 into 2 pi by kT h square is a constant, me star are also constant, and this term also constant. Hence, this can be written as sigma I is equals to A exponential of minus Eg by 2 kT, where A is equals to 2 into 2 pi kT by h square to the power of 3 by 2 me star ms star to the power of 3 by 4 E into mu E plus mu H. Right? So, this is the expression for electrical conductivity in intrinsic semiconductor. From this expression, electrical conductivity expression, we can also determine energy gap of the material. We can determine energy gap of the material. What is energy gap of the material? Energy gap is the energy difference between conduction band and valence band. Specifically, it is the energy difference between lowest energy level of conduction band to highest energy level of valence band. So, we can determine energy gap of the material from this expression. So, energy gap Eg. So, we can determine energy gap of the material. Again, here taking logarithm on both sides, we can write natural logarithm log sigma I is equals to log A minus Eg by 2 kT. So, if you plot the graph between log sigma and 1 by T, log sigma on the y-axis and 1 by T on the x-axis, it gives a straight line. Okay, so the slope is equals to minus Eg by 2k. The slope is equals to minus Eg by 2k. So, by taking the slope, we can determine energy gap of the material. From this expression, slope is equals to, we will take the modulus, because this we will get the negative slope, then slope is equals to Eg by 2k. From this, energy gap Eg is equals to slope into 2k. Here k is the Boltzmann's constant. K is 1.38 into 10 to the power of minus 23 joule per Kelvin. But you will get energy gap in joules. So, to convert joules into electron volt, then energy gap Eg is equals to slope into 2k by 1.6 into 10 to the power of minus 19. Then you will get energy in electron volt. So, this is the expression for energy gap in intrinsic semiconductor. So, in today's class, we have derived the expression for carrier concentration of intrinsic semiconductor. Using law of mass action, we have derived it. Density of electrons in conduction band and density of holes in the valence band. By taking those two expressions, we have derived the expression for intrinsic carrier concentration. Then Fermi level intrinsic semiconductor. After Fermi level intrinsic semiconductor, we have derived the expression electrical conductivity sigma and energy gap intrinsic semiconductor. So, with this, we have completed the intrinsic part. Intrinsic part. In the next class, we will discuss the extrinsic semiconductor. What are extrinsic semiconductor? How extrinsic semiconductors are classified? What is an N-type semiconductor? What is a P-type semiconductor? Those topics will be discussed in the next class. Yeah, thank you.
Like, share and subscribe. Hit the bell icon for more updates.